Right. But, okay, so today's N2E talk is on 3D representations and rendering and how they relate to robotics. So let's start with the what. So 3D representations, I'm sure we're all familiar with them. If you've ever, watched an animated movie or played a game, um, there's a long history of, as long as we've had computers making graphics. So it started with in the 1960s with mesh-based and point clouds. In the 1980s, we started seeing volume rendering, and now 2020, something called neural radiance fields were introduced, and in 2023, 3D Gaussian splatting was introduced. And so we're going to do a quick walkthrough of each of these, and then we'll focus a little bit on NeRFs and Gaussian splatting, and we'll have a demo as well. So mesh-based methods, you represent objects as a series of points, and typically you arrange those points so that they form triangles, and you form the triangles through rasterization. And from there, there's a lot of things you can do. It can be really simple and blocky, like the this dolphin in the top left. You can obviously see all the polygons, so it doesn't look very smooth. Um, and you see for the earlier examples, things may look angular and blocky because everything's formed out of triangles. But when you add millions of triangles, things look pretty high fidelity. So um, it started out with just few, and processing power really limited how many triangles you could put or how many polygons you can put into your scene. Um, we started figuring out how to apply lighting to this and developed what we are now calling, or now you would call physically based rendering. And one of the, I guess, most interesting or biggest developments in this side of things is just really highly optimizing your meshes for details. So the picture on the right is something from Epic Games, a technique they call nanite, which is um, sort of dynamically changing the resolution of objects to maximize performance. So these techniques are really fast. Modern GPUs can render like millions of polygons in a scene all at once. But the lighting is not always physically accurate. It's always an estimation, and it's usually like tuned and tweaked for artistic purposes, which is really great for that purpose. But it lacks fidelity in other ways. I'll also talk about point cloud based. So this is another representation where you just represent scenes as a collection of points. Um, it's not really directly useful. Like you're not seeing games or movies that are made of this, but it's highly relevant because um, when you're talking about structure for motion or LiDAR technologies, they will directly output a point cloud. So the top image is something that an autonomous vehicle will output as it drives down the street. It's sort of the lowest level features that you get, or lowest level measurements that you can get out of it. And I don't know how they might have captured the image on the bottom, but similar, like if you have some sort of LiDAR or laser range finding, you'll get a point cloud out. So that's another representation. And then these are also the two halves of representation is how you represent it and how you render it. So for mesh-based and point cloud-based, it's just rasterization. Here it's even simpler. It's just a dot on the screen where there's a dot in the 3D space. Now, volume-based representations originally were developed for medical imagery. So it was people had like CT scans inside the body, and it's like you have different mediums like bone and flesh and things like that, and you want to see how they intersect and their interface and things like that. And so the way you do that is consider the different materials to have different properties and how light would pass through them. And so um, you simulate the way you render these things is use ray marching or something like that. So you send a ray through your 3D object, and at each point in your ray or along your ray, you sample points and say what is the color and the density of the object at this point, and you add those up along the ray, And then it's like you encounter a lot of red things along the ray, and then the pixel corresponding to that ray is red. Um, so that's the way you render these things. Um, yeah, so originated for medical imagery, present, still used for medical imagery a lot, and probably other ways that I couldn't really think of, but it's also used a lot in video games and movies. So another example here is Smoke Grenade from CS2. It's simulating a lot of light interactions with the smoke. So, I mean, you can kind of see that the part that's out of shadow is lighter, and like deeper parts of the smoke are darker, and it's because light has to travel through more in order to get there. And so another thing that we're doing presently with volume based is we're rendering them the same, but instead of representing them with an array of discrete values or something else, we're representing them with neural networks, or for 3D Gaussian splatting, it's a different representation. Um, I did gloss over that. So the original volume representations were just arrays, like 3D arrays with discrete values. Um, you might also see things like signed distance fields or voxel representations, which is more akin to um, it's an abstraction. When you use voxels, it's an abstraction, and it gives you control in other ways, which may be useful for other things. But now let's get to the newest ways. We'll start with NeRFs. So NeRFs stands for neural radiance fields. Um, it's a volume-based representation where instead of using an array of discrete values, you use a neural network to store what should be at each point in 3D space. So each point in 3D space will have a color and a density, and that also depends on where you look at it from. So in this figure, which is from the original paper, which was published in 2020, you have a bunch of pictures of this Lego truck. And so you shoot a ray through the scene, and I hope my mouse shows up on the Zoom. I'm not sure if it does. So hopefully you can
Yeah,
follow
I see.
along. Okay, cool. So the ray goes through. Here it's empty space. Here it's empty space. Here it's empty space. But here it intersects with um, the yellow bucket of the truck, and it follows through. And similar here, you can just imagine that there's a lot of empty space, and then it encounters something that's dense and yellow. And so this is what the neural network is trained to output, is that in this space, output yellow. If you go to the treads, in this space, output black, etc. And if there's empty space, don't output anything. And so this is another way to look at this. So this ray, okay, so sigma is density. And so for most of the ray's travel time, the density is very low. It's traveling through open space. But then it encounters something. It encounters something that's colored brown, and it's high density. Um, so this ray, ray one, ends up outputting a brown pixel. In contrast, this one encounters an orange color, and so it comes out as orange. Also interesting to note is that there's two areas of high density here, but since this one comes first, this is sort of what the ray sees, and the second peak is sort of obscured. So I think the description here sort of goes over that, but it is using sort of classic volume rendering techniques. It's been optimized to be a little bit faster, and that's constantly being improved. But it's sort of taking an old idea and applying neural networks and deep learning to make it better. And so deep learning and neural networks makes it better because the entire process is you can backpropagate and optimize it. So I'll get a little bit more into that. But now we're going to go over 3D Gaussian splatting.
I'm not hearing anything.
You got it. Can you guys hear me now?
Yeah.
Okay.
So let's talk about some of the limitations of NeRF and how that motivates some of the optimizations we see in the 3D Gaussian splatting paper. So with NeRF, it's an implicit representation of the scene, which is very slow to optimize. When we have an MLP that we're using to learn the RGB and density values, we're basically learning it for every point in the scene, which means that we're learning points that have zero density, which is not what we want to do. Um, in addition, we're sort of parameterizing every scene we parameterize the scene in all locations. This isn't very efficient space-wise. So in order to make things more efficient, let's use an explicit Gaussian representation of the scene. So we're going to parameterize everything in terms of 3D Gaussian splats with means and covariances. And since we have much less parameters to optimize, this will be much faster than what we see with NeRF. A lot of current neural rendering work that you'll see in computer vision conferences such as CVPR use Gaussian splats. And we'll address this a little bit when we talk about current research. But to get into 3D Gaussian splatting, it follows a similar pipeline to what NeRF had, where we start with a set of images, we extract their poses, and then we have our 3D Gaussians, which we'll use to model the scene. We project those 3D Gaussians into 2D, and then we follow a rasterization process in order to produce an output image. And then similar to NeRF, we can backpropagate the loss between the ground truth image and what we just rendered in order to adapt and modify the Gaussians that we have in the scene. Now, another important process in 3D Gaussian splatting is adaptive density control. We want to have enough Gaussians that we're representing enough of the scene. But we also don't want to have too many Gaussians such that we have a lot of them to optimize. So depending on a couple of parameters, such as how many Gaussians do we have currently, how much space is each Gaussian covering, we can measure this by the covariance matrix of that Gaussian. We will prune the Gaussians in the scene and use that to optimize the final scene that we're reconstructing.
So these slides may be a little bit out of order. I'm going to talk about why we bother with this. So like I was saying, we've had 3D representations for a long time, and they can look pretty good and pretty convincing. But there are some reasons that you might want to have higher fidelity. So medical industry, entertainment industry, those needs have been addressed by the sort of classic techniques. Robotics, what we're seeing is that we want higher realism because we want our robots to be able to be trained in simulation and then put out into the real world. And so you really want to crank up like the realism in order to have that sort of direct transfer. Other things, virtual reality, digital twins, other things where you want high fidelity. And also the fact that these new methods have backpropagation, they're differentiable, enables some neat things that I'll talk a little bit about later. Two of the reasons, again, so realism, the picture on the left here is the original and the picture on the right is rendered. So it's can be really hard to tell like which is which because it gets really realistic results. And again, the differentiable rendering pipeline. I don't know if I have a slide that explains this fully, but oh, I do actually. Yeah, differentiable rendering. So there's a lot of images on this slide, but what I just want to say first is that differentiable rendering means that you have this system, you have this rendering pipeline where you have your NeRF, your 3D Gaussian splatting, and you say, I'm putting my camera here and I'm rendering an image in this 3D scene. And you want it to look, you want this view to look like something else. You have a ground truth. You say, I'm optimizing this. It should look like my ground truth. And you can backpropagate the error by comparing the image you render and your ground truth image, pixel to pixel. You can backpropagate that error throughout the entire rendering pipeline and change the weights of your network to basically see what you want to see. And so one application of that is that you have a 3D representation of like a robot and you have a ground truth for how you want the robot pose to be. And you have a 3D representation, and you compare what the robot looks like in simulation and how you want it to look. And directly compare those, backpropagate the error, and eventually your robot will look how you want it to look. So this is taking basically an image and converting it into robot controls, which is can be really powerful. This is a new paper, relatively new paper called Differentiable Robot Rendering. I don't know enough about it to explain it in depth beyond what I've basically just explained. Um, but if you want to learn more, it's linked here.
So just to go over some other fields that you might see NeRFs or 3D Gaussian splatting being used. For Ronan and Anis research, we're interested in the application of neural rendering for downstream tasks such as anomaly detection, change detection. But some of the other works that are highly relevant, the first one here being NeRF RPN, which appeared in CVPR. It's a general framework for object detection using NeRFs. There's also a paper called PAD, which introduces using NeRF for pose-agnostic anomaly detection. And the general gist of this paper is it's an inversion of the NeRF process. So instead of trying to render output images from a given camera pose, we want to find the initial camera pose that gives the ground truth image. And using that, we can align a potentially anomalous image with non-anomalous ground truth and use that to determine any anomalies in that image. There's also been applications of NeRF for SLAM. There's lots of papers that have appeared in CVPR, ECCV, and I'd encourage you guys to take a look at the websites for those conferences if that's the line of work you're interested in. In terms of general rendering and 3D Gaussian splatting, there's been an explosion of work in terms of relighting or remodeling scenes, combining things such as diffusion models and NeRFs, and using those to say, if I wanted to edit a scene and I want to add in another object, people have been doing that. But overall, neural rendering is a very, very popular area of research. And there's a lot that we could cover if we had more time. But for the limited time that we have, I would recommend that you guys take a look at the various conferences in computer vision if you're interested in seeing more.
Okay, now we are going to demo how to do this. So I don't know, again, like I said, there's a lot of hardware and software requirements for this. So realistically, it would be hard for people to follow along in real time. But we're going to go over it, and this is being recorded. So if you want to try, I would say you probably will end up having to look back at the recording and also investigate other methods if you don't have the hardware required. So let's see. Going over it, there's two options that we're going to cover right now, two different implementations. So there's Instant NGP, which comes from, it's NVIDIA's implementation. It trains really fast, requires an NVIDIA GPU greater than 1000 series. If you're on Windows, I think it's probably easier. They have an executable. If you're on Linux, you can build it from source, but it shouldn't be that hard. Instant NGP is good because it trains and renders really quickly by NeRF standards. You can get you can start seeing your NeRF actually look right within a couple seconds, which I don't know if it's that impressive, but the original implementations of NeRF would take hours or days, so it was a big step up. The other implementation we're looking at is NeRF Studio, which is a tool that implements dozens of models in an easy-to-use way. It also includes 3D Gaussian splatting. Also requires an NVIDIA GPU, probably. Some implementations might not require it. It mostly requires PyTorch being enabled, and then they have a faster implementation, faster training loop that requires libraries that only work on NVIDIA GPUs. So I haven't tested, there's like a million different ways that you could try to run this on different hardware combinations. I haven't tried them all. And there's other implementations that beyond these that are maybe better in other ways, maybe easier to run in other ways. But this is what we have set up, and we're going to run it. Also, I don't know if I mentioned, Instant NGP is only for NeRFs, in contrast to NeRF Studio, which has NeRF and one or two 3D Gaussian splat models. So there's also a little bit of data here that you can use if you want. We've confirmed it to work. So generally, when you're training NeRFs, you need a static scene. It should be well lit, in focus, and it should be static. So I have this scene from our lab. It's just a bookshelf. I just want to show you some of the images. So I think it's about 50 images that I took while, varying the angle from which I took it. And that's the data we're going to use here. So in general, there's two steps to training a NeRF for 3D Gaussian splat. You have to calibrate the images and then you train the model. So calibration involves taking the images and figuring out where they are in relation to each other in 3D space. That's basically a requirement always, regardless of what technology you're using. As far as I know, there are some that try to get around it, but in general, you're going to be calibrating your images and figuring out where they are 3D space. So looking at my demo here, I have some folders. I have my images here, which is the images in this drive. I'm going to be going over the NeRF Studio implementation. So NeRF Studio does have installation guide. It requires PyTorch and they recommend CUDA. So that is kind of a lengthy process. We're not going to go over that now. If anybody does want to try this and they are having trouble, let me know. I will definitely help you, but I just want to keep this concise for now. So for NeRF Studio, to calibrate images, oh, my screen sharing is paused. I was trying to share my VS Code where I have a terminal open. Let me change my settings. Right, okay. So yeah, I'm in a folder with all my images. I have everything organized in an images folder. That's the main one you're gonna start with, and that's the one I have uploaded. So the first step is, what is the first step? I'm blanking on it right now. NS process data. So this comes with NeRF Studio. So I have a on environment with NeRF Studio active. And so running this is going to look at all the images, use structure from motion and ColMap to figure out where all the images are in relation to each other, and we'll visualize that later. But it's finding the pose for the images. So this usually it can take a couple minutes to run. I don't think I'm going to let it run because I have this prepared ahead of time. But what you get is you get this, it produces this folder which has ColMap images copied and it has transforms.json. So let me see if I can just show what that is. So it's a bit hard to tell, but it's a JSON file and one of the entries, all the entries look like this. It has a file path, which is the image, and then it has a transform matrix. So transform matrices are 4x3 matrices that describe position and rotation in 3D space. So for all the images, it basically figured out where they are. Yeah. So once you have that, the next step is to do NS train and the implementation that you want to do. I guess I'll just show sort of why we use NeRF Studios. They have a lot of methods. So if you start looking into NeRFs, or if you have looked into NeRFs, you see a bunch of different methods that get developed. Instant NGP is re-implemented here. There are methods that are called splat facto, implement 3D Gaussian splatting. They have NeRFs that work with generative methods. And just a bunch of different things that come from research papers where they try to address a specific issue with NeRF, and they have different results. To actually train a NeRF, I believe that the command is just to tell it to train and tell it to look in the calibrated folder for all the images. And it'll start going. Nope. I type out. So the model we're using is NeRFacto. So it's, I think, a modified version of Instant NGP, which is NVIDIA's implementation, which has an emphasis on speed, and it just has a few other improvements tossed in there. So it's also nice because it has a viewer, a remote viewer, so I can open it up and visualize the process. I am running it remotely, so it might be a little bit slower than it would otherwise be. So all of these rectangles are where the images I took are in 3D space. And if I pan over to where I was actually looking when I took the pictures, the scene comes into view. And I can bump up the resolution and wait for it to render. While it's doing the training process, the rendering is a little bit slower than it would otherwise be. But we will compare this with 3D Gaussian splatting and see how much faster that is. So this is just a view. I'll wait for it to render so we can see it again. It's pretty good. It's blurry in a little bit of spots, and you'll of course notice that anywhere I didn't take pictures, it's completely noisy. So all the pictures I took were sort of focusing on this shelf, and it got a little bit of the shelf below it, but anything else is just completely random. You'll also see here, so these things that are being highlighted are the pictures I actually took. And you can click on these and see the view that is actually rendered. Again, it's taking its time to show the full resolution image. You can pretend it is. It did it a couple times. But anyway, that's how the training process actually works, is that it compares the view that you took, it compares the image you took to the render, and then it backpropagates the error, and then that's how you get your result. So I'm going to stop that for a moment. And instead, I'm going to run a Gaussian splatting model. So as we talked about earlier, NeRFs can be really slow. There's still reasons to use them, depending on your use case, but they are much slower when they're running. I am running this remotely, which, as you can tell, my computer is struggling to run VS Code, so it's definitely not running these NeRFs. So I'm using the SplatFacto model, which is NeRF Studio's re-implementation of Gaussian splatting. And it'll have a similar training process. All you need to do is change out that value, and it'll again start training. I'll refresh the viewer. Also, I'll mention that these things take some time to fully train. This is already at 3%. The NeRF house training probably would have gotten to like 20% in the time I left it running. I don't know, I didn't look. So they do take a little bit of time to train, but they start looking decent pretty fast. So I will now look over here. This not initialized properly. Oh. The viewer is being a little weird, and it probably has something to do with the fact that I'm using it remotely, but I'll give this a second. Yeah, okay, so this is a good view. Already, this has been running for like a minute, and it's looking pretty clean. It's looking cleaner than the NeRF was, and you can sort of see it updating faster. You can also see a little bit, it's kind of hard to tell, but you can sort of see the Gaussians that make up this scene. So when you have these like protrusions that are sort of like lines, these are just really thin Gaussian distributions. This is like its color is black and it's sort of stretched out like this. And you can see a bunch of these protrusions because the entire scene is made up of these Gaussians. So yeah, it's not running great on my viewer, but It looks pretty clean. I also don't know how it's going through the screen sharing. Um, but yeah, let me check really quickly if the other scene I was trying to prepare is ready. Um, these came from images like I was showing. You can also use videos and it'll process it in a different way. Yeah, so I prepared a video scene. This one might be tough, but I'll try to run it. And while I'm doing that, um, that'll be sort of wrapping up. So does anybody have any questions? Let's see. It's, I'm going to give this a second so that it can actually initialize. It does get to a pretty viewable state pretty quickly, but we'll see. So this scene was a video. Also, I haven't checked that this actually calibrated properly. If you try to run this, one thing you might run into is that Nurse Studio will say all your images are calibrated, but it won't actually be correct. So you have to be careful for that. Okay, cool. This is a video, so all the frames are much closer together. Um, Taken outside bush. I'll give it a little bit of time to render, but if you walk around bush enough, you've probably seen this. Just statue out here. So it's a good demo of an outdoor scene. Um, there are considerations to take with outdoor scenes, which I actually didn't take. So you can get better results. It's taking a little bit while to converge, but there's a lot more going on in this scene. Um, I'll come back to that before I end the call, but I just wanted to put up links for everything. So I have linked the Nerf Studio website, the Instant NGP website or repo, the original publications for 3D Gaussian splatting and Nerf, and the code for this presentation. So I think that's about it. And yeah, let's see. Yeah, you won't get the absolute latest methods if you're using Nerf Studio, but it's really convenient. So it's nice to use. And it is training pretty nicely. Um, you can also, so it's hard to tell because there's a latency between my laptop and my lab computer and the call, but it's 3D Gaussian splatting is rendering much faster. So like before it took the Nerf a couple seconds to render at full res. Um, but this is just sort of keeping up. It's almost real time. Some people are interested in 3D Gaussian splatting for video game graphics, which of course have like real time requirements. Um, and so it's kind of promising in that regard because it is pretty fast. Yeah. Okay, so I'm going to wrap it up unless we have any last minute questions. Thank you for listening. And yeah. All right, have a good one.